Hello, my name is Lennert Vanmunster and welcome to this presentation about our paper titled LightTour Enabling Museum Audio Tour with Visible Light. This was a joint work with Jona Beysens and Sofie Pollin from KU Leuven and Qing Wang from TU Delft. It might be a while since some of you visited a museum, so let's first refresh our memory. Basically, in a museum audio tour, each visitor carries a device that is used to play back audio tracks with information about the different museum pieces. We categorize the current state-of-the-art audio tour systems into 4 different categories based on their principle of operation. Category 1 systems are the simplest and currently the most widespread. In these systems, the audio is stored locally on the user device, and the audio tracks are manually selected by the user on this device. Category 4 systems, on the other hand, are the most advanced, and these systems combine wireless audio streaming from one or more nearby access points with automatic track selection based on the user's location. This gives Category 4 systems a greater flexibility and ease of use, since no manual user input is needed. The goal of this work was to build such a Category 4 system, but with visible light instead of radio frequency communication. We named our system LightTour. In LightTour, each individual ceiling light is one access point, which uses a white LED to both illuminate its part of the room and broadcast an audio stream to that part of the room. Each user device is equipped with a photodiode to receive this signal. First main feature of LightTour is that it provides a location-based service. This is because with visible light communication, we are able to achieve a very small AP cell size of only a few square meters, because the light itself is blocked by objects, and because the LEDs that we use have quite a high directionality. Each AP then simply broadcasts one audio track about one nearby museum piece, and each user device only plays back the received signal from the nearest AP. A situation that could still occur is that a device can be at the edge between two APs, and if those two APs would transmit simultaneously, a collision would occur. To solve this problem, each AP is also equipped with a photodiode that is sensitive to visible light, so it can detect the reflected floor signal coming from neighboring APs. This is this green non-line-of-sight signal in the figure. As a result, each AP can detect if neighboring APs are transmitting. Based on this principle, we developed an uncoordinated MAC protocol, which I will present in a bit more detail in a few slides. Then we come to the third feature, which is that LightTour also provides an infrared uplink channel using an infrared LED at each device, and the photodiode at the AP is sensitive to both visible light and infrared light. Finally, downlink and uplink transmission can occur simultaneously, so LightTour provides full duplex communication. This slide shows the biggest advantages of LightTour. Firstly, LightTour is very power efficient since the communication is piggybacked on the existing indoor illumination. Then, like I already mentioned, LightTour provides a full duplex link, and we think that the uplink channel greatly increases the power of the system for any future applications. An example of an uplink application that we implemented is one where the visitors can send short feedback messages about nearby museum pieces in real time to the nearest access point. Thirdly, LightTour provides a simple location-based service. Which audio track the user receives only depends on the AP that the user is standing near. Fourthly, the uncoordinated MAC protocol means that each AP can operate as a standalone unit. So LightTour does not require any central coordinator or any time synchronization between APs. And finally, the uncoordinated MAC protocol, combined with the fact that visible light communication only requires very simple transmitter and receiver front ends, means that LightTour has a very low hardware complexity. To make this all work, however, there are still 2 big challenges that need to be addressed. Firstly, this figure on the left shows a measurement on our testbed of the received signal strength depending on the horizontal distance between a transmitter and a receiver. The green solid dot on the left is the signal strength when the horizontal distance between the AP LED and its own photodiode is close to 0. So this is what we call the AP self-interference. The red curve is the signal strength of the uplink signal. As you can see, the uplink signal is much weaker than the AP self-interference. This means that full duplex communication would be impossible if the self-interference is not addressed. Then on the green curve, you can see that as we increase the distance between the AP LED and the AP photodiode, the reflected floor signal gets weaker and weaker. This means that the self-interference is stronger than the reflected floor signal between neighboring APs. Hence, due to the self-interference, while an AP is transmitting, it cannot detect if neighboring APs are also transmitting. So to summarize, the AP self-interference ruins full duplex and ruins collision detection. The second challenge occurs on the uplink. Because of the low transmission power of the user devices, they cannot detect each other's transmissions. This means that the user devices are hidden from each other, and this challenge will need to be addressed at the uplink MAC protocol. Okay, so now let's look at the different components of the LightTour system in a bit more detail. The LightTour protocol stack can be subdivided into three main layers: the application layer, the MAC layer, and the physical layer. The two main challenges are addressed at different layers of this stack. I will now present each layer individually in a bit more detail. The physical layer is pretty straightforward and based on the existing IEEE VLC standard 802.15.7. We use on-off keying with 4B 6B line coding on the downlink, and during periods when the AP is not transmitting any frames, the white LED just emits a constant light signal at half intensity, as shown on the figure. This way, humans cannot detect any flickering of the white LED. On the uplink, devices transmit short message frames using Manchester coding. Additionally, we also implemented a Reed-Solomon error correction code on the downlink to increase its robustness. To solve the first challenge, which was the AP self-interference, we developed a novel digital self-interference cancellation technique specifically for visible light communication. The microcontroller at each AP digitally cancels the AP self-interference, which enables the full duplex and the collision detection. The way it works is that the microcontroller computes an estimate of the self-interference signal using a model of the impulse response of the path between the AP LED and its own receiver. This path is shown in this figure. The microcontroller then cancels the AP self-interference by subtracting this estimated self-interference signal from the actually measured self-interference signal. The biggest challenge to this technique is that the computation time of the impulse response filter to compute this estimate of the self-interference signal is too slow to be performed in real time on a low-cost microcontroller. The way we solve this problem is by breaking down the impulse response into two components. Firstly, there's a receiver circuit, which is made up of a filter, amplifier, and analog to digital converter. And this circuit can be modeled as a static impulse response, which does not change over time. Secondly, the visible light channel itself can be modeled as a simple one-tap path loss, which can change over time. The computation of the static part of the impulse response is then implemented using a lookup table, which is very fast and only requires 2 kilobytes of memory, and the dynamic one-tap path loss only requires one multiplication. So, in conclusion, thanks to the unique properties of the visible light channel, which is that it can be modeled as a simple one-tap path loss, and the fact that the receiver circuit can be modeled as a static lookup table, the self-interference cancellation can be performed in real time on a low-cost microcontroller. So now let's look at the MAC layer. We developed a MAC protocol that we call Full Duplex Carrier Sense Multiple Access with Collision Detection and Hidden Avoidance, or FD-CSMA HA. On the downlink, this MAC protocol is equivalent to CSMA-CD, where the AP uses carrier sensing before transmission, and while transmitting the start of a frame, it performs collision detection to detect if they start transmitting at exactly the same time as a neighboring AP. This collision detection is of course enabled thanks to the self-interference cancellation at the physical layer. If a collision happens, both APs perform random exponential backoff. The collision detection enables reliable broadcasting since each AP knows with certainty that its successful frames did not collide with a neighboring AP. The second challenge, i.e. the hidden device problem, is solved at the uplink of our MAC protocol. All uplink frames can only be transmitted during the payload of a downlink frame. Additionally, interleaved with the data bits of each downlink payload, there are what we call short busy slots. While the AP is transmitting, it detects if the uplink channel is busy and dynamically sets these busy slots. Here, a low-high busy slot indicates that the uplink channel is idle, and a high-low busy slot indicates that the uplink channel is busy. Each user device then simply decodes the latest received busy slot to know if there are other nearby devices already transmitting, hence solving the hidden device problem. The user devices then simply schedule their transmissions using a random access algorithm similar to CSMA. Then let's finally look at the application layer. On the application layer, each AP broadcasts an audio stream about a nearby museum piece using an open source codec called Speaks. In addition, the APs use a leaky bucket algorithm to ensure that the audio frames are transmitted at the correct rate. The location-based service works by having each device measure the received signal strength of each audio frame in combination with a hysteresis mechanism to only decode audio frames from the nearest AP. Finally, on the uplink, user devices transmit short text-based feedback messages to the nearest AP. Okay, so now I will show you our testbed, which we used to perform our experiments on. We reused the white LED transmitters and photodiode receivers from our previous work, Dense VLC. Additionally, we use a simple infrared LED transmitter made up of an NMOS driver circuit and an infrared LED. Each AP and each user device is equipped with an Arduino Duo microcontroller on which the LightTour protocol stack is implemented in C. We use the onboard USART controller for modulating the on-off keyed signal, and we use the onboard ADC for demodulating the received signal. Additionally, we use other optimization techniques such as fixed point and direct memory access to enable real-time execution. Using these techniques, we achieve a data rate of 190 kilobits per second on the downlink and 71 kilobits per second on the uplink. This is comparable to the state of the art. Here you can see the setup of our LightTour testbed, which consists of 3 access points and 2 mobile user devices. And using this testbed, we were able to test most of the functionality of the LightTour protocol stack. And to test the protocol in an even larger scale scenario, we also implemented a large-scale simulator in MATLAB. Now I'll present the main results. Let's first look at the performance of our self-interference cancellation technique. The left figure shows a measurement of the self-interference cancellation strength on the 3 APs, depending on the vertical distance between each AP and the floor. By placing the APs at various vertical distances from the floor, we can change the amount of self-interference the AP experiences. The right axis, together with the orange curve, shows the remaining energy in the signal after cancellation. The left axis, together with the blue curve, shows the ratio between the amount of self-interference before and after cancellation. As you can see, a maximum of 30 decibels of cancellation can be achieved when the self-interference is very strong, which occurs when the vertical distance between each AP and the floor in our experimental setup is very low. When the vertical distance is closer to real-life scenarios, the remaining energy in the signal after cancellation is close to the noise floor. The right figure compares the computation time on the Arduino of our lookup table method to compute the finite impulse response filter with more classical methods such as multiply accumulate. It shows that our technique is about 75% faster, which enables the real-time execution on a low-cost microcontroller. In this slide, we show the performance of our MAC protocol. Here, the left figure shows the downlink channel utilization depending on the offered load of our MAC protocol compared to the CSMA-CA MAC protocol used in the IEEE standard. This experiment was performed on our testbed for 3 APs and in MATLAB simulation for 9 APs. It shows that our CSMA-CD gets a very efficient channel utilization, about 10% better under high loads. The right figure compares the achieved data rate when 2 user devices are transmitting to a single AP in our experimental setup. As you can see, the busy slot mechanism increases uplink throughput by a factor 2.5. Finally, we wanted to study the robustness of our system. To evaluate the robustness, we measured the accuracy of the carrier sensing and collision detection mechanisms when there is a person standing between 2 access points. Since in this situation, the strength of the reflected floor signal between the 2 APs is weaker. The right figure shows the measured false positive and false negative rate for the collision detection. The solid blue line is without blockage and the dashed line is with blockage. As you can see, the blockage increases the false positive and false negative rate. However, as you can also see on the curve with the circles, is that the false positive and false negative rate under blockage can easily be decreased by increasing the number of samples that are used in the collision detection mechanism. We performed a similar experiment for the robustness against ambient light interference and obtained similar results. So in conclusion, LightTour is a system that applies visible light communication to the application of a museum audio tour. Several new mechanisms for visible light communication were developed, such as the real-time self-interference cancellation, which enables the novel full duplex MAC protocol. We implemented and evaluated the LightTour system on a proof-of-concept testbed based on Arduino Duo microcontrollers and performed substantial evaluations on the performance and robustness of LightTour. I thank you for attending, and I hope you found this somewhat interesting, and I already look forward to any questions you may have.